training module 1. So this is going to cover the Thermino E and the ePV, which is our direct models. So basically one pipe in, one pipe out. The Thermino E is our grid electricity model, and the Thermino ePV is solar and grid. We're going to cover more of the technical side. So first of all, we've got health and safety. So yeah, that's obviously an over-exaggeration, but don't install the product outdoors. We do have obviously electrical element down here. You've got an electrical control box up there. We do advise it should be fitted in an indoor installation in a frost-free environment. So that's not to say you couldn't fit it in an outdoor outhouse, weatherproofed outhouse, for example. But one thing you'd have to bear in mind is the heat losses would be much higher. So if you're going to do that, so like you know what customers are like. They might say, oh, that's where I want it. I want it in this outhouse. That's where it's going. You just have to make the customer aware that their capacity, that battery, will not be as good as if it was fitted indoors. Because the last thing you want is for the customer to call you back, you know, the first cold day of the year saying that they've not got enough hot water. So it's our job to make the customers understand what they're buying, isn't it? So, so that's the first thing there. Yeah, don't tilt the battery during the installation process. So obviously the plumbers, like, nobody's got any steel toe caps on. It's just ridiculous. But the plumbers obviously got the painter and decorators involved in getting this battery up the stairs. I mean, what we do say is you shouldn't tip the battery more than 45 degrees. So 2 reasons for that. So if there's any liquid phase change material inside the unit, it may tip out the breather cap, and it'll, you know, obviously alert somebody to thinking that there's a fault. So the other reason is if you tilt it more than 45 degrees, you might get overwhelmed by the weight, because they can be quite heavy. So that's why we say you can find the sweet spot of the battery when you're tilting them, and you do get used to, you can maneuver them once you get your confidence about them. But I mean, if you think about this, they're dragging that up the stairs. They've got their dust sheet, which was good of them. But what they're going to do when they get up to the landing here, they're going to prop it up on its vertically again. They've just dragged that thing on its side all the way up the stairs. So yeah, not the best. So what we would advise is using proper trolleys. So for a ground floor installation, you can use a heavy duty trolley. So you would just get a sack barrel trolley that can cope with the weight. So that you'd have to look at the manufacturer's instructions for this, what the specification is. That's obviously a bit more of a heavier duty. And then you just get your ratchet straps and you strap the battery to the trolley itself, so it's not going to slide off the base plate here. If you're going to be going upstairs or anything, you know, I'd be recommending using a stair climber of some sort. I mean, this is what we have in our possession. This is from a company called Zonzini. We've got them on permanent hire. So the buddy lift, that can go up to a 210 lift going up the stairs. But any higher than that, you know, you need to be using the 300. This domino stair climber for the 300. If there's any stairs involved, because the 300 is quite heavy. So I mean, not that we're in cahoots with Zonzino or anything. I mean, they have done some work for us in the past where they'll do a white glove delivery service into the property. So they'll deliver it to the location as well. As long as that, like, the old cylinder's been removed, they'll put the battery into wherever you're wanting it, and all you need to do is plumb it in. So it's taking that hassle away. So they've worked some wonders for us in the past. But yeah, we've got that equipment to use. So install the product on a hard level surface. So this was an old cylinder that was in that had leaked, and obviously it's knackered the floor. So just put a bit of solid hardwood down, 18-inch ply or something should do the trick. 18mm, not 18-inch, and just support that floor again. All right, you wouldn't have to, if there was no damage to the floor, you wouldn't have to reinforce it or anything. Just for the heat battery, because the batteries are actually lighter than its equivalent cylinder when the cylinder's full. So you don't have to reinforce the floor or anything like that. Don't use detachable hoses to connect to the water mains. So the braided hoses, they can burst, they can kink. You can get the little, if you're running water through them all the time, you can get the little rubbery inside part of the pipework coming through. So we do recommend using rigid pipework on the heat battery itself. It can be quite tight, because the reason I'm saying this is we have had some jobs where installers have fitted a battery under a kitchen unit, and they've used detachable hoses to then pull the battery forward if they've ever had to work on it for any reason, like a gas cooker hose or something. So that's we don't advise that. Rigid copper into the unit. No hot works within a meter of the battery. So that's an installer's got a bit trigger happy with a blowtorch. A bit too close. The reason for that is we do, any heat, it can melt your Lamicell insulation, it can melt the plastic of the cell as well. So yeah, prefabricate any soldering before you insert it into the battery. Product's not suitable for tank-fed water systems, so we're converting from tank-fed systems to mains pressure. So this is quite important when you're doing your specification of a house. Does the customer have enough mains water? High enough pressure of mains coming into their property? Because I think most water companies, they'll set the standard as at a bar minimum that they'll ensure is coming into the property. So just bear that in mind. If the customer's at a ground floor flat, for example, and they've got a cold water storage tank up in the attic of that apartment block, they might be getting about 1.5 to 2 bar possibly. You convert that to mains, they might get less. So it's just something to bear in mind. So I've actually found this is actually just a UK thing. So when I deliver this to people that overseas, they see a cold water storage tank and they're flabbergasted that we still use this type of system. So yeah, we do like a bit of tradition in the UK. So water must be in the appliance before turning on the electricity supply. So what we've had in the past, we've had an electrician, the unit's arrived on site, the electrician will do their work. They'll put the power on just to test it. Brilliant, it works, but then they'll leave it on. And then a day later, the plumber turns up to connect up his pipes, and that battery's been running without that heat exchanger being pressurized with water. And we've had, damaged heat exchangers being sent back to us because of that. So just make sure that the water's on before you put the power onto it. Pressurize that heat exchanger. Don't stack the heat batteries with internal controllers. So, I mean, why you would want that in your house anyway is beyond me. I mean, that's monstrous. You've got plenty of space there on the floor to have that set up. So, I don't know. But yeah, like we do have some components inside the battery. We've got relays, got PCBs, we've got a temperature sensor. If you've got to work on that, you've got to have to remove that heat pump. So you're going to have to get someone who's F-gas qualified to decommission the heat pump to do a 2-minute job, possibly on the top of the battery. So it's, don't stack them. I mean, you could fit the batteries onto a racking system if that racking system can take the weight and the clearances for the battery are adhered to. So just don't stack anything directly on top of the other one. The product must be earthed properly. So again, this is amazing what you find in customers' houses as an earth. So that's our earth clamp in the battery. So that must be fitted. What the earth clamp does is it's completing the earthing circuit from the element to the main earth of the appliance itself. So if there was and I come across this quite a lot of installers don't install this, they just leave it sitting there underneath the insulation. But if there was ever a problem with the element touching earth and the customer didn't have their pipework bonded, for example, potentially that could be live. So you must fit this earth clamp, all right? The batteries must have a... Yes.
Oh, sorry. The earth, is that come from the unit itself? Excuse me. Does that come from the unit itself, or is that to come from the main distribution board? Or
So so you can see it's just tying into the side of the unit there, Adam. So that's just connecting onto our unit, and then obviously you put your live, neutral, and earth into the incoming supply, and that's how you go back to earth there.
Thank you for that. Cheers, mate.
No worries. The heat battery, you must have its own dedicated 16 amp breaker back at the fuse board, and then obviously if that's under that, you then have to investigate, is the twin and earth the right size? So you should have 16 amps here, your dedicated 16 amp supply, and then run it in 2.5 mil twin and earth from the fuse board to your double pole isolator where the battery's going to go. This is, you can fit timers, but this is a timer that's been fitted in line with the electrical supply. So if you think about it, when it was on its hot water cycle, the unit was powering up. When it was on its off cycle, the unit was powering down. So we need a permanent live to our heat battery at all times, so it can monitor the temperature. So what was actually happening in this case, the timer would come on, it would power up the unit. Brilliant. But then it would turn off, unit would power down, no lights on the display. But the customer would use their store, and then the next day, it would power up again. But the unit, the PCBs aren't very clever, so it couldn't recognise the drop in temperature, so it was coming up with a full charge. And the customer's running their water saying, my water's cold, why have I got a full charge on my display? And it's because that the spiking of the PCB was confusing the PCB, basically. Right. So basically, they were using this as an isolator, a timer as an isolator, basically.
Got a quick question with that?
Yeah.
Is that the same with the ePV? Because that's run off an eddy, isn't it?
ePV is a bit different, yeah. So again, we still need that permanent live into the battery, but we use a switch live or modulating live from your eddy or solar diverter.
Okay, Alex, so it doesn't need two ways on a consumer unit then.
No. It's just the set, yeah, single. We'll cover that as we go, Alex. It's just this is just a quick briefing, but that's your correct type of isolation. So for the Thermino E and the ePV, so say your Thermino E, that's just a 20 amp appliance switch double pole isolator. That's what you require, because remember it's a 16 amp minimum rated switch that we need. So if you search 16 amp double pole isolators, it starts coming up with rotary isolation switches and stuff. Your customer's never going to have that in their kitchen, are they? They've just had their kitchen installed and you've got a big rotary isolator on the wall. Not going to happen. So you go to the next level up, and it's a 20 amp appliance switch. That's what we'd recommend. When you're talking about the eddies and stuff for the ePVs, Alex, it's a double pole isolator that will feed. If you think about your flow chart, it'll be double pole isolator, eddy, then your heat battery. So that one isolator isolates the eddy and the heat battery at the same time. All right.
Does the same apply for? Just got one with the lime scale reducer, the electronic lime scale reducer, and does the same apply with that? So you've got your 20 amp pole double pole switch, and you can take off like something from that to feed the live for the descaler.
The descaler, you could just plug the descaler into the ring main circuit, Adam.
Yeah. So, I'm struggling with the location. There isn't one anywhere near. I could possibly run a fuse spur from it, but I was thinking that because it's only, I think it's 0.25 amps. It's tiny. Do you know what I mean? I wondered is that going to be okay? Do you think?
Yeah, that'll be fine as long as you're not going to exceed that 16 amp rating.
No.
I mean, because the units themselves, they'll pull about 13 amps, maybe a little bit more depending on what the incoming voltage is to the property. So yeah, if you're going to add a 0.25 amps, it's not going to make a difference, or 0.025.
That's what I thought, but I just wanted to double check. Thank you.
Yeah, that should be fine. Yeah. So yeah, some more questions here for you guys, so you can have a little look. Tell me what you think. Who wants to answer the first one? Where should the heat batteries not be installed?
Outdoor.
Yeah, perfect. Do you remember what would be the effect if you fitted it in a weatherproofed outhouse?
Reduce capacity because of their external
gloss, isn't it?
Yeah, heat losses, basically. Heat losses will be high. What angle should the heat batteries not exceed when being transported?
45 degrees.
Spot on. What should you do before supplying power to the heat battery?
Make sure there's water in it.
Yeah. What rating and type of isolator should be used when connecting the electrical supply to the heat battery?
20 amp double polar.
Yeah. Yes, I'll give you that. I'll give it half a point for the double pole. 20 amp. I mean, with the minimum rating is 16 amp. So we do this is quite an important one for me, because we do get some jobs where installers have used a 13 amp fuse spur, but because we'll pull about 12.5 to 13 amps, but we're just touching that rating, that maximum rating of the fuse spur, and what can happen is it can just scorch itself and become brittle and burn itself out. So you've got to up it. All right, so good stuff. So specification and basic operation of heat batteries. So this is just the table from our manual. Like I say, I've put in the most important parts to it. This table can answer a lot of questions that your customers will ask you. So obviously heat storage capacity in kilowatt hours to the water content in the heat exchanger, your equivalent cylinder size, the V40 volume. So we'll cover a lot of this as well. So heat storage capacity, 3.5 kilowatt hours. So for the grid, for all of them really, if you're charging from grid, for example, it'll take 3.5 kilowatt hours to charge that unit. So if a customer wants to try and calculate how much it's going to cost them to fully charge unit, it's going to be 3.5. Obviously, multiply that by your pence per kilowatt, and there you go. So whatever it is, 3.5 times, how much is it now for electricity a kilowatt? Is it 70 pence or something? I don't even know anymore. Up to 14 kilowatt hours there. So as you see here, 12.8, it was close, 12.7 I think I said. That's for the 300, so that's the amount of water in our heat exchanger at any one time. So that's why we don't have to comply with Legionella cycles. Your equivalent cylinder size. So obviously, yeah, 300 6-litre cylinder. We've got a Thermino 300, 210, 150, and 70. So the V40, what that is, so part of our system components, we'll strongly advise to fit a thermostatic blending valve on the outlet pipe, because you can have basically, once that battery is up to temperature, you can have up to 80 degrees coming out the draw-off pipe initially. So you also got to blend that down. It's an anti-scald device primarily, but secondly, if you set that TMV to 40 for 40 degrees on the outlet, you can increase the capacity of your heat battery. Because essentially what you're doing is, if you set it to 40, you're restricting the heat that's leaving the heat battery, and you're blending it down. You're restricting the heat, and you're adding a bit more cold water to the outlet. So that's how you can increase your capacity there. So, and this is based on a 10-degree inlet temperature from the street as well. So obviously, when we start going into the winter time, there's going to be a higher heat exchange going on, because the coal mains water temperature is lower. So this will be a little bit lower, but it gives you an idea of what the battery is capable of. I mean, we had a project in Guatemala, and they were fitting 150s, 150 EPVs. And their V40, they were telling us they were getting about 400 litres from that. They were doubling their V40 because their inlet temperature was 20 degrees from the street. So there was less of a heat exchange going on. So they increased their capacity massively. So it just shows you what you know, a 150, what size is that? 640 high, and you're getting 400 litres out of that. It's pretty incredible. So, and next week we go into our heat losses as well. So take note of these. So your 70, your 150, your 210, your 300. And what we can do is we can compare them to a cylinder on the next slide. So 0.48 kilowatt hours over a 24-hour period for a 70. What the customers ask us is, how long's my capacity going to last if I'm going to go away on holiday or whatever? So what you need to do is you take your kilowatt hours for that unit, 3.5 in this case, and you divide it by your 0.48. And what that does is it gives you your length of time in days from 100% charged to 0% depleted. So has anyone got a calculator handy? Does somebody want to do the calculation?
I have it down as 7.2916666667 for the 70E.
Yeah,
Is that correct?
so about 7 days. And if you
7
go up to
days.
if you do the 300, I think it equates to something like 16 days or something. Yeah, so it just shows you. So if say the customer's got a 300, they've got a full charge. If they want to go away for a week's holiday, they could turn it off on the timer, not use any electricity just to top it up, and they'll still come home with some hot water. Albeit it won't be a full capacity, but a lot of that's to do with as long as the pipework's lagged as well. There's another thing that we sometimes get is called thermal siphoning. So if you've got the pipework coming out and then going up vertically from the unit, you can get heat loss by means of conduction. So in an ideal world, what you want to do is come out and go down to stop that from happening. So, and also what I've also seen is, some installs, they come out and go down, but one of our components that we need to have fitted is a mini expansion vessel, a 0.5 litre expansion vessel. What some installers have done is they put a reducing T-piece here and they put the vessel on the top. So that vessel is basically acting like a big heat beacon, if you think about it. So really, the vessel should be fitted on that downward leg just to stop that, because you can't insulate. You can insulate the vessel to a point, but it's not going to be as great as having, the heat staying in here. The heat battery is a better thermal insulator than the lagged pipework, basically, or an expansion vessel wrapped in a towel, for example. So that's just a little bit of advice.
Secondary returns on these. So circulated hot water, you wouldn't recommend that?
You can do them. I mean, as long as the customer just understands that their energy costs will be a bit higher with that one, George. So, like with any secondary return, I mean, what I have seen some customers do is they'll put their secondary return on in the morning. So they'll isolate the pump basically. And when they get up in the morning, they'll put the switch on. That'll activate the pump, get the secondary return up to temperature, and then they use their hot water. When they're finished, they just turn it off again. Or that pump's controlled by a timer or something, just to try and stop, because you could have that pump running constantly, and your energy usage. I mean, if you've got a secondary return, then you can obviously afford the energy usage, can't you? It's the size of the house that you're in, but you can do it as long as the customer understands about energy costs and how much it's going to cost them a bit more, basically, because you've got to get that up to temperature. So your secondary return is going to have to be above 55 on the return. I mean, what you could do, so you could obviously have your main unit here, and at the furthest point from the house, you could have maybe a 70, for example, and then that could boost it at the far end of the house, and then obviously circulate back. So it's like you're splitting the difference between the two sides of the house instead of relying on that one unit. So that's another way around.
We've used heat maintenance tape in the past because it's tapping time, so it's hot water out the tap within a minute is what it's for. So we've used heat maintenance tape to overcome that. Yeah. Instead of secondary returning everything. So
So I've never seen, is that like a trace heater or something?
Sure. It's like trace heating tape. So
is it? I think you've got to get hot water at a tap. Is it within 30 seconds?
I think it's within a minute.
Is it a minute?
At a certain temperature. So
certain temperature, right?
It's the trouble is when you've got very low flow outlets, you're obviously it takes an awfully long time to discharge the pipe work. So overcome it with that or with the secondary return. But thank you.
No, you can do it. You just got to be a customer aware. Speaking about pressure, minimum supply pressure 1.5 bar coming into the property. and we've got a maximum of 10. So this does annoy me, because what we sort of contradict that slightly by saying if you're exceeding 5 bar coming at the property, or you think the property is at risk of exceeding 5 bar, you should stick a pressure regulating valve on your water supply to limit that pressure to 5 bar. What we're saying here is the heat exchanger can take 10 bar. So say, I don't know, you've had a failure of the pressure reducing valve, and you've got a 10 bar expansion relief valve on the pipework somewhere. The heat exchanger will be able to take it. But if you're going to keep supplying that heat battery with 10 bar of pressure, it's obviously not going to be that great for it. So what we ask is for people to limit it to 5, and you should be plain sailing from there. We've got a 2.8 kilowatt element. I don't know why the comma's there. It should be 2,800 watts, but it's essentially a 2.8 kilowatt element. So again, if you're using your calculations, using your heat storage capacity, so again, use the 150, 7 kilowatt hours, you divide that by your element size of 2.8, that gives you your charging time from using the element. So from the 70, does somebody want to do a 150 calculation just whilst we're in the zone? Does anyone manage to divide 7 by 2.8?
2.5.
Excellent. 2.5. So what we look for across the board is your 70 is about 1.5 hours, 2.5 hours, 3 hours 45 minutes, and then 5 hours for the 300. So what you have to remember though is with your charging times, if that battery's been in a warehouse or something, it's especially in the winter time, that block of PCM is going to be much colder than it would do in an ambient setting. So what I'll explain this a little bit as we go as well, but that initial charge time might take a little bit longer, because the element, it cycles on and off during the first startup, because what it does is it will charge up. The temperature sensor will recognise that the base of the battery is hot enough, and it cycles off again. So it does that off and on scenario. We call it a soft overheat, until that heat starts to circulate around the battery, until the middle sensor starts to detect it. Once that middle sensor detects that temperature rise, then the element will then stay on. So what you'll notice is when you first turn it on, you have your power LED and then your amber LED, which is your element. That element LED will go off. You wait 5 minutes and it will come back on again. And it dances off and on like that until that temperature starts to circulate within the battery. So there's no fault there. It's just to let you know that's what happens. And everyone's favourite, the product weight. So they can be quite heavy. So that's why I was explaining earlier about using proper equipment for transporting them, especially doing your first one. Because if you get a battery delivered to the customer's house, that's just going to arrive curbside on a pallet. So you've got to think, how am I going to get it from the pallet into the customer's house? Is there any steps leading up to that house? Is there a threshold, like a plastic threshold, I need to get over? Are you going to damage that in any way? So these are all the sort of things you need to do in your assessment. Because the last thing you want to do is break a plastic threshold of the customer's door, and then you're the one that's going to have to fix it. So there's your profit from the job, just going into the customer's door. What we'd recommend as well, if you're going into an airing cupboard, so you transport in with your trolley, and you can use squares of thick plywood, like 18mm again, we've used in the past. Put the plywood down on the floor, and then you can walk it on the plywood. You can slide it on the plywood into position. And you can use a couple of sheets, not massive sheets, but just squares that are just bigger than the footprint of the battery. So you can get it off, and then you can slide it from that bit of plywood into the location. Saves you having to slide it on the customer's floor, basically. And again, ruining a threshold at the airing cupboard. So it's just some tips that I've picked up myself over the years. Speaking of footprints, the depth and the width, we're always going to be 575 deep, and we're always going to be 365 wide. It's just the height that changes with the different sizes. So the Thermino 70, where are we? Yeah, 440 high, up to our Thermino 300, which is just over a metre tall. So that's our sizes. So again, bear in mind, if you're thinking about putting this in a cupboard and there's like fixed shelves above the unit, we need a 450mm clearance above that, because this lid, it pulls forward and lifts up, and then you can lift the lid off, but you still need a little bit of workability just to do your wiring inside the unit as well when you're commissioning it. So just bear that in mind. Clearances to the side, if you've got your pipes and your cables come out the right here, you need 150mm. So obviously you'd have 150mm, and then there's not enough space there to fit your TMV, but that's as a sort of minimal requirement. All other sides you would have 10mm and 10mm back and left if you had a right hand side exit entry. We always need about 150 on the front. You see that little cover plate there? Behind that cover plate, there's a mechanical overheat thermostat, so it's manually resettable. So if the temperature sensor is not pushed fully home, the unit might overheat. So obviously to reset that, you need to get access to this panel. It's going to be quite annoying if you've butted it right up to a wall or something, and you can't access it. So just bear that one in mind as well, all right? Has anyone got any questions on this slide before we move on? All good.
The only thing I was going to ask is the inputs on the 300 EPVs, the E, they've got 2 water in and out. Is that correct?
Yes. So we'll cover that, Alex.
Okay.
In the next couple of slides.
I'll wait.
Well, you're jumping the gun. You've seen this before, haven't you? You know the answers.
Well, no. I've had a look.
Yeah. No,
Just got a quick
yes.
question, if that's okay. Can you go back to the other slide, if that's okay?
Yeah, sure.
Yeah, sorry. It was the clearances. So this is like really popular, obviously, as a replacement for the cylinders, because it can fit in a hellishly smaller, dimensions room, And this particular job, which I've got one for recently, it's the only position is underneath the kitchen work surface, in a cupboard. I spoke to the technical guy, Ivan. He's really cool. He was really helpful. He said, make sure that we can move it, make sure they can remove it. So to get away from that 450 to pull it out. Going back onto something he did say earlier on, you did say do not put the flexible adapters on it. He sort of said do use flexible adapters, which I was quite confused about. However, I found a way around that. I'm going to use some compression elbows and bring it down within this 500 unit. And then also something you were talking about, the plywood. This is going in a kitchen with hard floors, and there's like these appliance rollers that add about 30 to 35 mil on. I've sat it on them and it just rolls really, because the 150E that I got, nearly 140 kilos. I also had to take that up 4 flights of stairs as well, and that was
by yourself.
No, impossible. Impossible. I've got a brother that's quite strong and he helped me, but it was these things that weren't made clear. It was a little bit of a rush job, but they weren't made clear. But just wanted to share my sort of findings with a group as well, and find out ways around it, because it's fantastic. I've seen it in person. It's really good, the 150E. Hopefully it functions correctly when I pipe it up and wire it up and stuff. But yeah, the weight is something to be looked at. It's heavy.
With that, I mean, you can't, obviously, if you carried it, I mean, fair play to you guys for doing it. If you didn't have any of the proper lifting gear, you can use lifting straps.
Well, we did, to be fair, we used the technique. We had a sack barrow that was capable of lifting the weight and more, and then I ratchet strapped it, just as you said. I had the bottom with some straps, lifting straps, and he had the top. So yeah, we sussed it but it would have been much easier with one of them. Also.
I mean, with that type of install, I mean, what you could, we do need that rigid pipe work. I mean, what you could do is would there be any space for isolation valves and compression? So you could technically
that's what I'm going to do. I'm going to isolate it in the cupboard next to it, which is underneath the kitchen sink, and then I'm going to put all the gubbins there, you know, the reducing valve, the expansion vessel, all that, and isolators and drain points as well, so we can drain them 2 legs. And just as you were saying about the heat beacon, you know, great, I'm coming down first to go across, so it's working out all right, to be fair. It's really, really informative. Thank you.
No worries. I mean, if you're so in that case, you would isolate it, you would drain off the standing water inside the pipework, and then disconnect it. You could pull it forward that way.
It isn't going to drain the actual, you know, did you say it was the sorry, I'm trying to look, it's the 3.2 litres, the 150E. It isn't going to drain them 3.2 litres in the unit. That isn't going to be a problem, is it? You know, it's not.
No. I mean, what you would do the only time you'd be wanting to remove that is to inspect the electrics at the top unit that are based up here for whatever reason. So unless the customer was going to move it or do something else with that space, so that's the only time you'd remove it. So as long as you can isolate it and disconnect the pipework safely, you can then roll it forward, and then you can work on the top quite happily. So
that's my plan. I'll send some pictures to the company once I've done it, just to make sure everything's sweet and that. But you know, it's a tough one. It's a lot easier than a horizontal cylinder. Anyway.
No, you know what? I'm really impressed that you guys have done the groundwork and how to make this work with complying with our requirements. Because a lot of installers, they would just drop kick a heat battery underneath a kitchen unit and just leave it. I know, and then everyone's got to pick up the pieces afterwards, no access to the pipes.
With all respect, they're too expensive to do that with. Jesus.
I know, but I don't know. Some customers got too much money, or some they get an installer that doesn't care. So it's really encouraging to hear we've got good guys on the call today that know what they're doing. So perfect, man. Thank you. Going on to this is a cylinder manufacturer. I don't want to mention their name, but it shows you obviously they've got their models 70, 125, 145, 170 up to the 300. The important one here for me is the standing heat loss row, as you've got there. So again, if you look at the 70, 0.91 kilowatts an hour that their cylinder would lose over a 24-hour period. So if you look at ours, you know, we're almost half of what a cylinder's capable of doing. And if you go way up to where are we? There's 300 litre, 1.69 kilowatt hours over a 24-hour period. And we are miles less than a kilowatt hour. So our units are much better thermal insulators than a cylinder ever will be. And we can prove that here. The other important thing is you've got your where are you? The V40, as we said there. So there's not much difference when you look at the 70 litre cylinder. Yeah, we're 105 litres to their 78. So there's a bit of a difference. But when you go up to their 300, you know, we are 436 litres compared to their 241 down here. So, you know, the proof's in the pudding. The advantages of take away the weight thing, Adam. But you know, looking at the weight, weight full, where are we? So just as a sort of caveat, there's your full weight. If you were to carry a cylinder that was filled with water up the stairs, you're 339 kilograms compared to 220. So, but yeah, granted, they are heavy, and that's what I'm saying. You know, I'm not trying to pull the wool over anyone's eyes. If you're dealing with a 300, you've got to treat it with a bit of respect, especially going upstairs. I mean, I've seen 300 in attics before, and I'm like, what the hell is going on here? How did they manage that? You know, you speak to the customer, like, yeah, they used a winch and then they swung it across to the edge of the hatch, and the guy had to drop it right on time. And I'm like, oh, it's just an HSE disaster waiting to happen. But yeah, just think about it. I mean, if the customer's wanting a 300, say the customer's in a I don't know, 4-bedroom flat or something, and they want a 300, you might have to fit 2 150s to get that storage capacity. So that they're the kind of things you've got to consider. Is a 300 going to be suitable for that property, or the access to that property? You can always find a way around it. A 150 with a 70, that'd equate to a 210, for example. Wire them in series, plumb them in series, or whatever, and that's a way around it as well. So this is a basic cutaway of the batteries. Essentially what we've got is our heat exchanger there, so that during the build, heat exchanger gets put in there, so it's just a coil of copper that's got these aluminium fins. So that sits in a plastic cell, and what they'll do is they'll pour the phase change material into the breather cap, and that then envelops the heat exchanger. So that's your direct, so it's in direct contact with our heat exchanger. There's no secondary source for that. And then the element, that's fully embedded in the bottom here, direct as well. So that heats up for the bottom and just starts to nucleate the phase change material as it goes. So
can I just be a real annoying interruption again?
Not at all.
Sorry, I do apologize.
Okay.
Pour the phase change material. So if you had it in its liquid form and poured it, I'm assuming, I mean, it must be like 95% of the weight of this thing is the phase change material. If you could get that portable and manageable and take it up in, I don't know, obviously biohazards, I don't know how that would work, but if you could transport that in manageable lumps, it would make it a hell of a lot better to situate.
Yeah, I know.
Does that sound?
Yeah, no, and it's a very valid point, Adam. It's the material scientists, that it's something that they have considered in the past. So, but how do you do it? I mean, you've got the logistics of that would be a nightmare. So we would have to have a company. Imagine you've got a top floor flat. How do you run a hose from the ground up? Are we going to rely on the installers to do it themselves? I mean,
the warranty factor sort of thing, you know, like if they do it wrong, or if something else goes in there, like you say, drop kick some pack of crisps in there or something like that. Yeah.
Exactly.
I know what you're saying.
We've got people tinkering with the. So really, what they've done is they're treating the heat battery like a barrel of Guinness. You know, they're filling it at a point of manufacture and distributing it that way. I agree. It can be it can be a pain in the neck. It just means that we've got full visibility of what's going into the battery. I'm not relying on external sources to do that. So, and then, you know, if you're going to, I mean, if for a 150, I mean, you're going to, how do you get that phase change material from the ground floor to the top floor? Because it has to be in its liquid form as well, which means it's going to be hot. You know, so you're going to have to do a few flights.
That's the thing I didn't understand about them hand warmers, though, that when it's in its liquid form and it's ready to change its state, and then you've got that activator, that the hand warmers are cold.
But then when you activate that chain reaction, that spark within the hand warmer, it solidifies, and that's it releasing its heat.
Yeah.
So
could you not transform it in the liquid form that's cold? I don't know if it's the same stuff, you know. I'm not trying to pick fault, I'm just trying to.
Yeah, that's a question for materials. My phase change material knowledge stops at slide 4. I'm afraid these guys know. These guys know that what makes it tick. I mean, I've seen them. I mean, I've seen them do the filling on site and on some of the batteries, you know, in test houses and stuff. Oh yeah, we need to add a little bit more of this phase change material in. They have to keep it up to temperature when they're applying it. So it's a bit of a. I mean, there'll be ways about it, but yeah, I think at the moment, if you've got a proper stair climber, you know, depending on what battery you're fitting, and you make the correct provisions that way, you know, you're never going to have a problem. Yeah, obviously, a bit of an experience lifting a 150 all the way up 3 flights of stairs.
It hurt me mentally and physically, I tell you.
They do, they can do. But you know, it's a learning curve, and next time, you know, it'll get better and easier. But no, it's noted. There is something they've looked at before, but they've just decided not to. So
yeah, thank you. Sorry about that. Cheers.
It's all right. Don't worry. Yeah. So your element is basically based here, 10-year warranty, and it basically charges for the bottom up. So this is quite an important thing to remember when you're piping up the units. So for a Thermino E, port, God, I can't remember now. Port A, sorry, is your inlet, and port A is your outlet. Whereas when it comes to the ePVs, it differs. It's port A is your inlet and port D is your outlet. So the reason for that is a Thermino E is charging bottom to top, but it's discharging top to bottom. So that means water comes in for the top all the way to the bottom, and then it comes out. So they've figured out that's the best way for the E to work when it's discharging its temperature. So, and a lot of it's to do with set points as well, which I'll cover. But if you think about that, so that phase changing material, it's fully up to temperature here. That cold water is essentially being preheated as it goes down. So if you were to look at the 3 temperature sensors, that top sensor is the first one to lose its temperature, and then it will start to obviously preheat. So this is what I'm saying about capacity. If you've got customers that aren't using their heat battery properly, you know, they're not. They might still think it's an immersion switch, for example. I'll put the immersion on for an hour, and then I get hot water. That's how we used to do it. I've done that for 50 years. That's not how it works. If you put that on for an hour, you're only half charged. So if you think about that, that water's only being preheated until you get halfway, which means you will get hot water, but you might not get, say for a 150, you're not going to get you might get a bath, but then you might not have enough to have a shower afterwards or wash your dishes. So it's all about quite a few jobs I've been to. That's the way customers have been. They've got a complaint about capacity, and they just haven't been running it for long enough, or they've got a timer set for an hour or something, or they turn it off and they turn it on when they need it. It's not how it works. So it's just something to bear in mind. Speaking of which, here we go. Heating element comes on. We charge from the bottom up, bottom to top. So that's what I'm saying. That temperature sensor string, we've got a bottom, a middle, and a top. The bottom one's going to heat up first, and that's where you get that off cycling, off and on, until that heat starts getting to the middle, and then the element will then stay on fully. But this is a Thermino E. It basically, cold water comes in at the top, exchanging its heat as it goes down to the base of the heat exchanger, and then it comes out hot. So if you think about that, if the customer's used half their capacity, that water's only going to start getting preheated here instead of up at the top. So the ePVs are a little bit different. They discharge bottom to top. So basically they start discharging from the bottom up. So the reason for that is it's all to do with the set points, and I'll explain that a little bit later. But it's so the unit can, if you're discharging from the bottom, that bottom sensor recognises there's a massive drop in temperature straight away. So what the unit does, it recognises that, and then it makes itself available for solar. So the set point's a lot higher. So a Thermino E, if you discharge 20% of your capacity, it then generates a demand. With an ePV, if you discharge 5% of your capacity, it then generates a demand. So that's the reasoning for that there.
Sorry, just on that point, can you limit it just to taking solar during those hours? So during the daytime, can you stop it taking from the grid? Yeah.
So that your Eddy would do that, Alex.
Right. Okay. So that's all set on the Eddy. There's no settings on the Thermino to run any of the timings or anything like that.
No, it's all from your external sources. So Eddies or volt-free contact timers for the Thermino E. So your Eddy, you'd have to. Again, this is where the customer comes into managing their own usage. So in the summertime, they might not want to have a time boost set.
Yeah.
But come the winter time, they're going to have to. You're never going to have enough solar to.
Yeah, exactly. And you presumably get a low off-peak tariff in the middle of the night, which is what we do with solar, so they can charge up then.
Yeah.
The rest of the time, it will just run off solar to tap it up in the daytime.
Yeah, exactly. That's all done externally though. Yeah.
Great. Thanks.
So we've got some more questions for you guys. So I'll let you have a little read. So what's the storage capacity of a Thermino 150E? Anyone?
200-ish.
And it's a bit of a trick question. So we talk about storage capacity, we relate to kilowatt hours.
Seven.
Okay.
7, perfect. What changes with the size of each unit? Is it the footprint or is it the height?
Height.
Yep, perfect. What's the calculation for charging time?
Power times kilowatt hours.
Anyone else? What
Capacity divided by kilowatt hours.
Kilowatt hours divided by power of the element.
Yes, that's the one. But yeah, so the kilowatt hours capacity divided by the element size, basically. So what's the calculation for working out days until fully depleted?
Is that storage capacity
Storage
divided by heat loss rate?
Yeah, spot on. Absolutely spot on. Yeah, divided by the element size. Yeah. Excellent. Good stuff. Has anyone got any questions on that bit so far?
Obviously, storage capacity, you've listed it at 40-degree outlet.
Mm-hmm.
So a 30-degree delta between 10-degree cold in, 40-degree out.
Mm-hmm.
Obviously, at 55-degree outlet, that pushes that delta to 45.
So that's...
So it's reducing the capacity. So, for example, the 300 at 55 is what, about 260-ish litres?
Yeah, so it's going to be, if you've got that TMV set at 55, George, yeah, your capacity in litres will be less.
Yeah.
But if you've got your TMV set to about 45, 48 degrees on the outlet, you will achieve that 300 litre mark.
Cool. I know 40 is like a standard that cylinder manufacturers use to give. It's like a heat pump at 7 and 35, isn't it? It's the standard kind of thing. Okay.
I mean, if I was to say to my wife, you need to have a shower at 40 degrees, she would just look at me with that funny look that they give you. So
it's a lot of shower mixers ask for an approach temperature of 55 in order to work the cartridges properly. So it's a bit low sometimes. You find you get issue occasionally, but do you publish those figures or is it just work it out, just use the maths?
What's that, the figures of this?
The figures obviously at different outlet temperatures.
No, we don't. So again, the outlet temperatures can vary as well, obviously, with flow rates, if it's not being commissioned properly, and inlet water temperatures and stuff. So we tend just to stick to the 40. The 40 that's the manufacturers go to, as you said. So hopefully it's just give you an idea of what the unit's capable of.
Okay,
George. I mean, again, as you said, if you've got a TMV set of 55, 55 is too hot for me. Not any skin left after that. I think even when you start getting up to 45, for me it's too hot. But again, it depends on the customer. They want to have the skin taken off their hands. I mean, the amount of times I've had to turn TMVs down for customers in a house, and then you start asking them, say, "Oh yeah, my hot water is quite hot." Like, well, turn it down. Just turn that dial, and it's because it's up to them. Oh, and always get them to check it as well, see to make sure they're happy with that temperature. There's no point in setting it to 40. Now the customer's saying that's not too hot. That's not hot enough for me.
No.
So yeah, mechanical connections. So we've got a little bit of flow rates here as well. So yeah, I think it was you, Adam, asked about the earth clamp. That's the earth clamp there. So that just ties onto the side of the casing.
Much clearer.
Yeah, perfect. So you've got Tektite elbows in here. So they're fully rotatable. You can have a left or a right or a rear exit. For this is just for the Thermino E7150 and the 210 models. So that's what we call a single port, one pipe in, one pipe out. You can also see the temperature sensor here as well. So that's a dry pocket, and what you have to remember is just make sure that temperature sensor is pushed fully home. You can see the little white marker there. That's generally your guide, but you do know when if you take it out and you push it back in again, just if you ever do have to take it out, which you shouldn't, just try and remember to feed it in gently. Use two hands, don't bunch it up because you can maybe break the sensor wire that's in there. Just be gentle with it. And yeah, you do feel that it gets pushed. Once it's pushed fully home, you do get the sense it can't go any further. So, but you've got your flow rates here for each of these units. So we've got, for a Thermino 70, we recommend a maximum flow rate of 6 litres per minute, 150, 15, a 210 up to 20. The 70, I mean, for me, that's not usable for having a shower, 6 litres per minute. That's more for your like static caravan type thing. You can push it up a little bit to maybe 8, possibly 10. You just have to be aware, the faster that water's running through the heat exchanger, the less chance it has of catching the heat. So again, you could be introducing capacity issues for the customer, especially in the winter time. That coal mains is colder coming into the property. Okay. I think someone mentioned about the 300s. So yeah, and obviously you've got your inlet pipe and your outlet pipe there. So inlet pipe, cold water is A, outlet on D, hot water. So for the 300, they'll always come as a dual port, so 4 pipe connections. You can get a 25 litre up to a 25 litre per minute flow rate, but what you do, you basically converting these 2 ports to a single port, as you see here. So that's like a branch, and you're basically just twinning the inlet points to the heat exchangers, and you're twinning the outlet point of the heat exchanger as well, and converting that to a single port. If we go to the next slide, you'll see these are the kind of prefabricated branches that should arrive with the 300, the 300E and the ePV anyway. So it consists of 2 pairs. One branch is for the rear, one branch is for the left or the right exit. So you can see the one branch, the short, we've got a short narrow, and we've got a long narrow, and we've got a short wide, and we've got a long wide. The going out the back is the wide section, and going out the side is the narrow section of pipe work. So you can have, you could have a left exit using the short branch, and you could have a rear exit using the long branch, basically. But if you're going to go out the one side, say the left side, you'd have the short narrow and the long narrow to convert that. So one thing to remember is, if you get a 300 and these branches haven't arrived on site with the unit, get in touch with your supplier, because they will have been supplied to the stockist. So they've maybe just forgotten to put them on the pallet or with a delivery or something like that.
And presumably you can run these as 2 separate systems as well, instead of just using the branches.
Oh, so, is this a space heating question?
Well, not necessarily, just for 2 supplies.
We wouldn't recommend it, Alex. So you're talking, in theory you could, but you wouldn't have to with a 300. The 300 would be able to, it should be able to basically provide for 2 different outlet points, if on at the same time. Your pressure, okay, your flow rate is going to be reduced to about 12.5 litres, depending on pipe runs and stuff. To be honest, I've seen it before with a Thermino 70. Someone's done that, and they've had 2 different outlets. So one outlet feeding the old Thermino 70s used to be dual ported. So and we've stopped doing that now. But what they did was they put one port feeding the shower room, so sink and shower, and then the other port feeding the sink in the kitchen.
Yeah.
And what they were getting is, if somebody was running the shower at the same time and running a basin of water, it was just killing the capacity of that. I mean, that was a 70 though, but if you're going up to a 300, you're hoping that you've got the capacity there to deal with it. One thing you would have to bear in mind is you wouldn't have the flow rates as well. So if you'd have to reduce that flow rate running through the heat exchanger.
The twin ports there's presumably two heat exchangers inside the battery.
Yeah.
Are they sat in the same place, if you see what I mean?
Yeah. So
they're not taken from the cold bit and the hot bit. They're taken from the whole capacity of the battery, each heat exchanger.
Yeah, if we go, so let's go back to your cutaway. Yeah, so it's the whole capacity heat exchanger basically. Yeah, so if you think about the pipe work, there's just an extra coil for that secondary heat exchanger running through the copper fins and stuff. So it's all part of the same heat exchanger block. If
and
that's
it
what you
follows
mean, George.
the same path, as it were. Both heat exchangers are kind of matched.
Yeah, exactly. So if you're plumbing into A and B, you're discharging from top to bottom.
Okay. Yeah.
If that makes sense. So again, yeah. So basically, if your A and B is coming in here, that's essentially what you're getting top to bottom. If you're cutting it and releasing out that way. But yeah, just remember, get in touch with our stockist there. The E's, it's a little bit different. You've got the inlet port, cold water inlet into D, and outlet on A. So the flow rates are the same as well for each unit. So it's just one thing to remember. If you're used to fitting E's all the time, you come across an ePV, just double check the manual, because you might think, I've been used to fitting Thermino E's all my days. Cold water goes into A and hot water comes into D. It's different for the ePVs. So just double reference the manual. All right. And it's the same for the 300 as well, for the ePV. You branch the two heat exchangers together, but just on different ports. Does that make sense for everyone? Yep. Good stuff. So got a few more questions here, guys, so I'll let you have a look at that and then we can talk about the answers. Does anyone have a crack at the first question? What are the pipe connections for a Thermino E?
A and D.
Which Gary, which one's your cold inlet, which one's your hot outlet?
The inlet's A and the outlet is D.
Yes, that's correct. Perfect. So what the pipe connections for a Thermino ePV?
The other way around.
Yeah, spot on. What's the difference between a Thermino E, a Thermino 300 and the other sized units?
The dual port.
Yeah. What must always be supplied with a Thermino 300E or an ePV?
The extra pipe work.
Yeah. Copper T branches. There you go. Spot on. So, has anyone got any questions on the previous slide so far? All good. So, we'll crack on a bit. So, traditional house there, you've got your cold water storage tank in the attic, open vented cylinder, pipework going all over the place. So, you've got risk of poor flow rates, water pressure, which will be poor showers. That situation, I'm thinking of like a flat, and you walk into the bathroom and the ceiling's been lowered. That's where the customer's cold water storage tank is, and they've got a cylinder on the same floor in a cupboard in the living room or something. Terrible water pressure, terrible head of water pressure. So then obviously you've got potential high heat losses from cylinders here. I mean, it breaks your heart when you open a cupboard door and you see something like that. The customer loves it because they've got a nice warm place to dry their clothes, not really understanding the concept. So with your heat battery, you're taking all this gubbins away, converting everything to mains and making the plumbing system much tighter, much more efficient, more direct. I mean, I had a job recently where an installer's phoned up and he fitted the battery downstairs, but he's kept all the original pipework running through the attic and everything, running through the cylinder cupboard up into the attic and then back around again. And what was happening was the battery was having to go all the way up to the attic sorry, the draw off for something to go all the way up to the top and then back down into the kitchen. So it's a massive loop, and the customers can again complaining about the time it was taking to heat and also capacity. So if you think about that, if you've got a big leg of pipe there, that's that energy for the battery sitting in the pipework, not getting used. So you want to try and make that more direct, don't you? Which is another important point. When we talk about the blending valve, we advise having that blending valve fitted as close as you can to the battery. So we've had some jobs where the specification engineers haven't specified a blending valve at the battery, and they've relied on the TMV below the bath and below the sink in the bathroom. That's great for the bath and the sink in the bathroom, but there's nothing downstairs. So you've got that raw thermal energy coming at your downstairs toilet tap and the kitchen tap. So basically depleting the battery faster. But also if you're running the bath or the sink up here, you've got your blending valves, that's brilliant. But again, you've got that pipework filled with that raw thermal energy for the battery, unblended. So it just creates capacity issues for the customer. So yeah, blend the valve as close as you can to the battery, blend it down, and then you've got less wastage of heat basically run through the house. So yeah, your EPV, we reckon you can generate 65 to 70% of your annual hot water demand from PV alone. So yeah, the batteries will be good for passive house properties as well. There's no external heat source, so obviously PV on the roof, that's great. Preheat to a compatible combi boiler as well. So the idea being, the battery gets charged from your PV, comes out hot, runs through the boiler. The boiler doesn't fire up, and then you've got obviously hot water coming out your taps. So one thing to remember though is check with the boiler manufacturer in this configuration, check what the maximum inlet temperature is on the cold water inlet, because some manufacturers will only allow a 15-degree maximum inlet temperature. And if, obviously we're going to exceed that, so you'd have to blend it down. But I think the Rooster 8000s nowadays, you can have a preheat quite happily. Was it the Alphas as well? So obviously catching on to that idea. But if you don't have as much PV being generated, again, the tension of the battery is starting to drop. The boiler will fire up, but at a lower gas rate. And then it's just making up the difference. So instead of firing up for 30 kilowatts, it's maybe only firing up for 10 kilowatts an hour. So again, the customer's still making a saving there. If you want this configuration, but the boiler manufacturer doesn't allow it, that cold water inlet, you could fit a 5-port solar blending valve. That's one there. So the blending valve, it's an external component which can prioritize the heat batteries store. Then once the battery's depleted, it then switches over to the boiler circuit, and then the customer gets the combi functionality. So I see a few jobs like this. The customer doesn't have a time boost setting. They just rely on the solar for the summer, and they might get a trickle charge of solar in the winter, but it's the boiler that's picking up the heavy work throughout the winter, and they're happy with that. They're still making a saving. And that's pretty much your pipe configuration. So obviously you just plumb both the boiler and the heat battery into the blending valve, and then you get your mixed outlet. And it's the blending valve that prioritizes. But yeah, so there's always a solution, basically, is the point here. So some installation considerations. So we've talked about sort of existing pipe diameter runs and stuff, making this plumbing system more efficient. Hard water areas, if you're exceeding about 150 parts per million, we do recommend having some form of descaler water conditioner in there as well. High pressure, so you're converting from a low pressure system if it's tank fed to high pressure. So you've just got to be aware of any lead pipe, poor fixtures that might be in the property as well. So you might have if you convert it, the customer might get a leaking tap, or the ball cock in the toilet might start passing as well. So again, it's just need to make the customer aware. system components from ourselves, pressure reducing valve when the incoming mains pressure is going to exceed 5 bar, or you think it's at risk of doing that. So you fit a pressure reducing valve. Expansion relief between 6, I would say 6 bar. We do say between 6 and 10, but if you think about it, if you've got a pressure reducing valve and you set it to 5, that fails. You're going to allow that pressure to go up to 10 bar before it starts relieving the high pressure. I'd want that relieving much faster than that myself. So yeah, expansion vessel, 0.5 litre, always required. And the TMV is always required as well. It's an anti-scald device primarily, but as we talked about earlier, you can increase your capacity. So we get a lot of questions about the expansion relief. I mean, that's just a flow group manifold. You can use that as long as you, but your termination point, you can just terminate that into a waste pipe. It's not like it's not like G3, you've got to have a ton dish and you've got to upgrade it to a bigger size pipe, run it to outside and terminate it, surrounded by a cage or anything like that. And it's not like a boiler PRV where you've got to run it independently to outside and turn it back to the wall or anything like that. It's just water pressure. It's not temperature related. So you could essentially just run that into a waste pipe in a customer's house. So take away the manifold block for a second. You've got two separates. You've got a separate pressure reducing valve and a separate 6 bar expansion relief valve. Say you had your pressure reducing valve at point of entry into the house. So let's go back to our interactive house. So you've got point of entry, you've got your pressure reducing valve here, and you've got your heat battery here. You could essentially fit your expansion relief underneath the kitchen sink here, teeing off the coal mains and just tying into the waste there. And that's a way around it. Does that make sense for everybody? Because we get a lot of calls and people get hung up on they've got to have the pressure relief valve beside the battery and like, where am I going to terminate? I'm going to have to lift the floors and everything else, but you can fit that anywhere, and that means as long as it's downstream of any non-return valve and upstream of the battery, you're fine. So that's another thing as well. If you think that the property has a non-return valve for any reason, we do recommend having that expansion relief valve fitted. Again, downstream from the non-return valve and upstream from the battery. Your pressure reducing valve, that's a non-return valve, isn't it? So just a couple of installation considerations to bear in mind. Who wants to go first? Disadvantages of a traditional cylinder from the slides that we just looked at.
Low flow rates.
Yep. Anything else? Think about when you open up that cupboard door.
Heat loss.
Yeah, you got a sad looking cylinder. Perfect. Yeah, that's the one. What must you check from the boiler manufacturer before plumbing in a Thermino ePV?
Maximum inlet temperature.
Yeah, spot on. What device can be used to integrate a Thermino ePV in a combi boiler that cannot accept a preheated water supply?
5-port mixer.
Yeah, that's the one. What external plumbing component is always required?
Expansion relief.
Expansion something.
Relief valve.
Yeah,
It's the expansion vessel, isn't it? 0.5 litres.
Yeah, that's the one. Anything else?
Pressure reducing.
Non-return valve.
What?
Blending valve.
Yeah, I was going to say, what might you get sued with if the customer burns himself? So yeah, blending valve, anti-scald device. Yeah. So vessel. So in an ideal installation, if you've got no non-return valves, you've got guaranteed 2.5 to 3 bar pressure coming in the property. All you're ever going to need is an expansion vessel and the TMV. What device is required if there is a form of non-return valve fitted on the coal mains?
Is that the PRV set to 6 bar?
Yeah, that's it. So I was going to say, someone mentioned it in the first set or second question. Oh, yeah. So that's everything there, guys. So yeah, spot on. Anyone got any questions from what we've just covered? All good. Okay. So the electrical connections. Thermino E with no timer. So that's what you're going to see. So the unit itself, it's provided with a 3-core flex, 2.5mm 3-core flex. So you've got your permanent live coming in, neutral, and obviously earth. Permanent live comes in, powers the circuit board, but the link here links that permanent live across, and then hits our relay there. So we've got 2 permanent lives essentially coming in. And that's without a timer. So the charging links is in place here. So with that setup, that just means that the customer's basically got a hot water constant situation. They'll deplete their battery by 20%. Battery will recognise that, and it will bring the element on and top itself up. Thermino E with an external timer control. This is a volt-free contact timer because this, you would wire that, the control circuit for that, into terminals 1 and 2. So terminals 1 and 2 is a volt-free circuit. So you need a volt-free contact timer. So don't apply power in here, otherwise the board will just explode. So you've got a 16 amp 2-pole isolator here, feeding our permanent supply. You can piggyback off that if you need to power the motor in the timer, as long as the contacts are volt-free. I can't emphasize that enough. But the timer is really the master. So even if we generate a demand here, it's going to be the timer that's going to dictate whether the element comes on or goes off, because we're completing that control circuit for the element. Your ePV, it's a little bit different. You can see we've got a 4-core flex here. So you've got a permanent live, a switch live or a modulating live, a neutral, and an earth. And you can see that charging link is in play as well, constantly fitted, because we need to complete that control circuit to tell so the unit can tell itself that it's available for solar, basically. So if you don't want to remove that, just keep that in. I think that's one of the software updates. I think they've actually disabled that functionality. So even if you do remove that, it still fires up. Don't take my word for it. Just don't remove that link. That's basically what I'm saying. But the wiring of your eddy, for example, you've got obviously power coming in, permanent live, which powers up your eddy. We piggyback off that. So again, if you think about our 4-core flex, your brown is tying into the permanent live of your incoming supply, the eddy. And your black, which is your switch live, goes into heater 1, your neutral goes into neutral 1, and then earth obviously goes into earth. And that's how you wire it up. So that's the wiring of your eddy. So just remember, we get a lot of issues where installers have put the brown, the black, the neutral, and it just, it doesn't work. So our eddy, you could potentially fit 2 batteries to an eddy. So obviously heater 1 we go into L1 and N1. That'd be your priority battery, and then obviously secondary one. With that configuration, we'd recommend having it plumbed in series. So if you think about your outlet battery, so obviously you've got 2 batteries, you've got an inlet going into your first battery, and then obviously your second battery's got your outlet. Your outlet battery, if you think about that, that's going to be your priority battery. So you'd have to wire your outlet battery into L1 and N1, and your secondary battery would be your inlet, and that would be L2 and N2. So that's how we do it. So just in case you ever had any problems with if you're the other way around, if you ever had any problems with your secondary battery on your outlet, your primary battery would have to preheat that first battery before the customer will get any hot water. All right, so does that make sense?
flow rate wise,
You
that,
do get a,
calculating just off your primary battery.
pardon me, sorry?
If you've got a 150 primary battery,
Mm-hmm.
You can do 15 litres a minute.
Mm-hmm.
Obviously, if you have a secondary battery that's a 150,
Mm-hmm.
you're still only calculating to deliver 15 litres a minute because you can't guarantee that secondary battery. Would that be right?
So you'd have to, again, it's all depending on your incoming supply as well, George. So you do get a pressure drop across the heat exchanger,
Yes.
which is it is in our manual.
Okay.
On a chart, so we can at the end of this we can quickly bring it up just to show you. But yeah, it's for 15 litres per minute, something like 0.2 of a bar or something pressure drop. So you'd have 0.4.
If you're designing that system, you design it with the 2 batteries, and you're obviously, how are you designing that, if you see what I mean? Because the customer wants the water they want, so you've got to deliver them whatever 15 litres a minute at 40 degrees. What's the purpose of having those 2 batteries? And it gives you somewhere else to chuck your spare PV if you've got any. Is that the sole reason for it?
That's the sole reason. If the customer wants to, but I mean, you could have, so say instead of having 2 150s, you could have 1 300.
Okay, and then it gives it just more to go at, basically.
Yeah. Again, it's what I was talking about earlier. If you're upstairs in a flat, for example, and you can't get a 300 up there, you might have to fit 2 150s.
Yeah. And
that would be your answer. So that's the purpose. Yeah, it just means that you can have, or if you wanted, I don't know, another battery fitted elsewhere in the house.
Okay.
Something like that. What you'd have to remember is the Eddy, though, it does prioritise heater 1.
Okay.
So once heater 1 is up to temperature, it then starts charging heater 2 for 15 minutes, and then it checks heater 1 again. And it does that. It goes back and forth like that until both batteries are satisfied.
How does the Eddy know what temperature it is in the battery? Does the battery just, obviously all it's got is alive? Yeah.
So it's exactly it. So it's a flow of electricity. So if you've got a flow of electricity, the Eddy recognises that.
Yeah.
And then when you're up to temperature, that flow stops, and then it thinks maximum temperature reached. Flick over to the second one. Okay. Which there's a very important thing with that as well, which we'll cover during the commission. So obviously setting a hot cancel delay. So what the Eddy does, as I was saying, we've got a soft overheat. So when the batteries, the sensor detects that the battery's too hot at the base of it, so it cycles off the element and it allows it to cool, and then it'll come back on again. With the Eddy, as we're saying, it recognises the flow of electricity, whether something's reached temperature or not. So if on its off cycle, the Eddy will then recognise, oh, there's no flow of electricity, maximum temperature reached, but it's not the case. What the hot cancel delay does is it tells the Eddy to ignore that message for whatever time you set. So it's just to stop customer complaints, basically, because customers are like, they'll look at something for about a month until they're happy that it works properly. So if they're looking at an Eddy, they'll say, why have I got maximum temperature reached here? But what the Eddy does is it this is how we set it here. It basically just ignores that message. So quick video here. So you go into your, I think this is the old firmware. What we say in our manual, set it to 45. But what I would say for the 210 and the 300, set that to 60. Just give it that little bit extra. Because it's bigger, it'll take a little bit longer for that heat to start flowing and circulating through the battery. So that's important. And then obviously you've got the other things as well, like set your time and date. Initially set your time boosts if the customer wants one set, and then that should be you for any off-peak tariffs. Any questions on the previous slides?
Lots. but but I think that's good. I think it's the basic information, but there's a lot of things to consider there with the electric side of things, isn't there? It's you know, the eddy obviously does a lot, but like you say, it's a lot to take in, that, isn't it?
It's a busy slide, to be fair. I mean, the eddy, we don't. It's not our device. You know, it's a popular device to use, and you know, we do a lot of technical support for My Energy because a lot of people fit the eddy with the heat batteries. So people fit new installation and think, oh, there's no hot water, sun amp. The phone sun amp, and it's actually the wiring of the eddy or how the eddy's been commissioned. It's not being commissioned properly with a wireless configuration, or the wires aren't connected properly. You know, is the CT clamps on the wrong way round. You know, things like that. So yeah, there is a lot. It's like one of these things, Adam. Once you do it more and more, you get used to it. It can become second nature. You know exactly what to command. Yeah.
I've got one of these coming up. That's all, and the customer was absolutely stringent on the electric side of it. She's wanting to install initially the sun amp. I think it's the 150 ePV she wants, but she's not going to have the solar installed and straight away. So it's like a year or two down the line. Is that going to be? That's going to make it a little bit more confusing to make it. No,
not necessarily. So the way to look at that install at the moment is the eddy is just a big fancy timer.
Yeah. Okay. Yeah. Makes sense.
And then all you're doing is you're charging it from grid until she gets her solar fitted. So
yeah,
if she can utilise an off-peak tariff, even better. But I would definitely. Do you know what size of battery she's going to have fitted?
I think it's the 150. She's only got one bathroom. And it's just going to have a bath and then over bath shower in it, so it's not too extravagant. But yeah, 150 ePV, I think it is. Yeah.
So with that, you probably want to have a time boost set in the morning between, I don't know, 3 and 6.
Yeah.
You know, for 3 hours. And then that means that the customer's going to have hot water for them getting. Obviously, you set the time boost around the customer's schedule.
Of course, yeah, but it wants to be ready for the demand, doesn't it? Prior to the demand. Yeah. That's exactly. Fine. But 3 hours is the rough timer just to keep it. Yeah.
I mean, it should take about 2.5 hours for a 150 fully charged, but you just set for even if you can set for 3 hours, but the unit might only be charging for an hour and a half or 2 hours. And reach
same again with that live flow of electricity. You know, the eddy will allow it to go, but obviously if the heat battery doesn't want the energy or it's full or whatever capacity, it'll stop. It'll stop itself within the electronics of the sun amp heat battery itself.
Yeah. So the heat battery will recognise it's up to temperature and basically break the circuit of the electricity flow.
That makes a little bit more sense.
Yeah. So yeah. Well. Again, just that's the only thing to remember is just get the time boost set, because if you just set it constantly on, or the customer just relies on just pressing the advance button, it will either never reach temperature or it will just constantly charge. So what I get was, I'm glad that you're fitting an eddy. You've got some form of control in there. Some installers they'll link that black and brown together. So. You know, that switch live is now a permanent live, and then the unit's just constantly charging, so then the customer has no control over their energy usage whatsoever. So, and then you get that customer complaint as well, saying, I've ran a basin of water and I'm using electricity, what's going on here? It's because the set points are higher as well for that. So it's better for me, I'd prefer having some form of control so I can control what's going on with my energy usage instead of just letting it just run away.
Would you still recommend that for just the E then as well, or would you still some control with the zero faults? Okay.
I would something that, I mean, because that, especially in this day and age with energy prices and stuff, you know, you could say a customer, you're gonna have it. So that timer is going to be set for 150, say 3 hours in the morning, and I don't know, an hour in the evening, for example. They know they're only going to be using 4 hours worth maximum of electricity that day. You know, and that's if the battery's been fully depleted. They might not utilise all that 4 hours, but it's also giving them the option, if they have a heavy hot water use day, they can advance it if they need to as well.
Yeah, yeah.
It just gives the customer more control and visibility, and it saves that complaint. You notice I keep reverting back to what the customer wants, and it's the customer rules our world, don't they?
Yeah. They do pay us as well.
Exactly. Exactly. So the customer rules our world.
Yeah, yeah.
So yeah, so basic sequence operation here. So again, back to this cutaway. So the temperature sensor, which is here, goes all the way down to the bottom there. So the temperature, put power on, pressurize the heat exchanger. Temperature sensors detect a demand for heat by means of resistance. So we've got 3 NTCs in here, and they'll be obviously high resistance, say 12 kiloohms. We need that's generating a demand. So the PCB reads the resistance of the sensors and sends power to the element relay. That then power is then sent down to our element via an overheat thermostat, which is wired in series. Element comes on and heats the PCM up to temperature. The sensor resistance changes due to the heat being generated, so that resistance then lowers. And then the PCB stops sending, once it's up to temperature, PCB stops sending power to the element via or it de-energizes relay 1, basically. And with the heat battery fully charged, the initial outlet of the hot water temperature will be between 70 and 75 degrees. So that's why you need that blending valve. The soft overheat, again, you've got your 3 temperature sensors. The bottom sensor will reach temperature first, due to being the closest sensor to the element down here. This stops the battery from overheating and allows the base of the battery to cool on its off cycle. Once the base of the battery has cool enough, that's a little typo there, the element activates once again. Once the heat starts to circulate around to the middle sensor, the element will stay on until fully up to temperature. And that's your basic sequence operation. Any questions on any of that? All good. So, Thermino E with no external timer fitted, what's going to happen? So you've got your lighting sequence here, you've got your power LED, you've turned it on for the first time, and your element LED is now active. What you'll see with that is LED D5 on the PCB illuminated. That's telling us that the battery is detecting a demand. So what that will then do, it will then energize the coil of the relay. So this is a DC relay, so that's going to be 12 volts DC coming from this point. Energize, and then that'll close the relay, which will then send power to the element. So if you look at, again, if you're looking back, that permanent live going to that relay, as soon as we close that relay, it sends power. And then if we get up to temperature, we break it. And then your LED D5 will go off as well. With a timer, similar rules apply, but again, we're detecting a demand here. We've got LED D5 illuminated. Nothing's happening. You know, we've got power here, permanent live at the relay, because our volt-free contact timer hasn't made its circuit. So as soon as we do that, then everything starts happening. Power starts flowing where it's meant to go. If that timer was to break, we still have that demand there, but it will stop sending power. It will de-energize the relay, which will break the circuit. So ePV. So yeah, we do have a 4-core. Don't be fooled by this at the moment. But yeah, so we've got a permanent live coming in, powering the PCB essentially. All right, so this scenario, what will happen is we don't have any PV being generated. So if you look there, we've removed link 1 between L1 and L2. All right. The heat battery is up, detecting a demand for heat. So LED D5 again is illuminated. That's now energized relay 2, but there's no power coming in anywhere. There's no power coming down L2. to then feed that switch to the relay. Once PV's been generated or there's a time boost set, that's when everything starts happening. So your power's now coming down that switch live, the black wire, feeding L2, which is feeding the switch of your contactor. And because the contactor, the relay's closed, it sends power to your element. Once the heat, essentially the heat this is the heat battery up to temperature now. So LED D5 has went off, and we've de-energized that coil of the relay. You can still have power coming down here, but it's not going to go anywhere because we've broken the circuit. That makes sense? How's everyone finding that? Silence is golden. So your basic equipment for commissioning fault finding. So that's all you're ever going to need for working on a heat battery. Maybe a terminal screwdriver or something at some point if you're working on the replacing a temperature sensor, which is a 2mm flathead for working on for removing the screws. But yeah, initially water pressure gauge for checking water pressures, standing pressure, working pressure. So again, you could have 3-bar standing pressure, but because the plumbing circuit is all over the place, you might open up a tap and it drops away down to 1.5. You know, pipe size reduction, pipe length, and all that. So this is a massive indicator for what the customer's plumbing system looks like. So it's a good thing to have your tool check, because really you want to start the job off on a high. You want to say to the customer, look, this is what I found. We may have to do X, Y, and Z to bring your plumbing system up to standard, instead of fitting the heat battery and the customer's complaining afterwards. Foot pump for checking expansion vessel pressure. So we do recommend that you've got that the customer should get that vessel repressurized every 2 to 3 years, because all that's in there is an air charge, which means that's going to dissipate over time. So if you lose your air charge, you lose that expansion quality, which means you could be introducing water hammer to the system as well. Digital thermometer for checking pipe temperatures. Obviously, outlets of your TMVs and outlets at your tap as well for the customer. Flow cup or a weir gauge for checking flow rates. Multimeter for checking voltages and resistances. And 3mm Allen key for removing the screws. That's all you're ever going to need. So that's a temperature sensor. It's an NTC type. So again, you've got your bottom, your middle, and your top in there. So they are all marked. This is the old money. So now we've got Thermino 70, 150, 210, and 300. The third generation was a unique 3, 6, 9, and 12. I don't think they've changed the labeling on it. So if you ever have to replace a sensor, just make sure you've got the correct size. Because if you go one that's too long, it will never reach temperature. If you go one that's too short, it's just going to overheat. So you have to make sure you've got the right sized sensor string for there, as it says there. How to check it. So there's 3 sensors in there, again, bottom, middle, and top. If we go back a little bit, let's see, back to a picture of a circuit board. So here, so there's your sensor connections here, 1, 2, 3, and 4. So what we would do is use the yellow as a common, and blue is the bottom, red's the middle, and green is the top. You would check yellow to blue, yellow to red, and yellow to green. And that'll give you your temperature sensor. That'll give you your resistance readings for each layer of the battery, bottom, middle, and top. So
what's the resistance, Steve?
So ambient temp, what is it, about 12 kiloohms, I think, when it's cold. So if you're up to temperature, that's going to be about 1.4 kiloohms. This will be about 1.5, 1.6, and this will be about 1.6, 1.7 when it's up to temp.
Okay, thank you.
So this is actually a good way. part of your commissioning, I mean, maybe what you should have in here is a current clamp as well, because once you're commissioning it, unless you can see what's going on inside the battery, it just looks like a box with lights on it. You can get your current clamp, you can check your element live, make sure the current's flowing, so you know that the unit's generating heat. Another way to go about it is check your resistances. So you know, if you check after, so you could do your start test. So you could check yellow across blue, yellow across red, yellow across green, and note them down. Note down your resistances. Leave it for half an hour. You're tidying up, doing your paperwork or whatever. Go back to it, turn the power off, check across yellow across all your 3 sensors again. See what the difference is. You know, if that resistance on T1 has reduced, you know the heat's going in there. And it's just a case of saying to the customer, just have to give it a bit of time. If you want to spend an hour on site afterwards, you can check T2 later. And then when you see that reduction in temperature, you know that heat's starting to circulate around the battery. It just gives you an indication to give you the confidence that the unit's working and performing before leaving. Because I know a lot of these jobs aren't around the corner. They can be 2 hours plus away from your house. So, you just want to make sure that everything's working correctly before you leave. So how do you check it? Set your multimeter to resistance, yellow across blue, 8.9 kiloohms. So this is a temperature sensor sent out from a battery. So when I've done this test, this is the ambient conditions that the sensor is being tested under. So yellow across blue, 8.9. What do you think yellow across red is going to be under those same conditions?
Should be the same.
100%, yeah. And same, yellow across green, it's going to be the same. So, but that's how you basically check it anyway, all right? Checking so this is actually an AC relay. All our units now will be supplied with the DC. It's just in case you come across one of the older units, it may have a white relay in there, which will be is AC powered. So how to check it? Yep. So obviously it's just got a coil in there. So if you're getting a problem with the customers not getting hot water, you suspect that it's not sending power, you can check the relay coil. You should be getting about 4 kiloohms across that coil. If you're getting intermittent overheating, temperature sensors pushed fully home, you could be getting a sticking relay. So with the power off, you should be getting continuity, but if you're having that scenario with intermittent overheating, what we do is allow the battery to charge a little bit, allow some heat to be generated within that relay, and then do the same test. And if you're getting any form of resistance across those 2 contacts or 4 contacts, then you know that there's a sticking relay, or it's allowing some form of electricity through if it's a bit sticky. It should read open circuit. Your mechanical overheat stat, so you can see there, that's the limit. So it's going to overheat at 96, and you'll be able to push that button back in when it reaches 90. So it's just a mechanical reset. You can remove it, just remove the 2 screws there in the housing and check across the contacts, and you should be getting continuity. That's just the resistance of my leads here, but you'll get continuity across there. If it's pushed fully home and you're getting open circuit, you know there's a problem with overheat stat. But generally, the problems I've seen with these is the gas within the file is released over time, and then the thing just constantly trips. So you can just get a faulty overheat stat as well. So your AC relay, sorry, DC relay, pardon me. So again, that's your AC relay is fed from these 2 points here. So that's a 240 volt AC for the white relay. The new units will be fitted with this black relay, and that's fed from here, which is a 12 volt DC. Okay. When checking across the coil of that, again, you should be getting about 85, 86 ohms across the DC coil. An element check, you should be getting between 18 and 17.5 to 21 ohms, live and neutral. That's just checking from the top at the relay, so that's checking the wires from the top down to the element and back again. Overheat start tripping. This is the fault scenario you'll have. You have a power LED and element LED on, but no hot water. So it'd be a case of check your overheat stat. Has it popped? Press it back in. The next thing to do is make sure your temperature sensors push fully home. If it's pulled out any, it's just going to overheat. I mean, that's a bit extravagant, but I have seen them completely removed before. Remember, remove the link if you're fitting a remote timer. Otherwise, the link will overpower any, take priority over any timing cycle. User interface, yeah, you've just got flashing lights as we go, demand for heat. One thing to remember with their ePV, it's always going to be looking for solar. So that element LED will be illuminated more often than not. And it's just to advise the customer that's normal operation. There's no fault, it's not using any electricity, it's just making itself available for PV if it's being generated. And obviously, flashy lights.